Our next speaker is Peter Wadhams from the University of Cambridge, and he's going to talk more about the ice, I think, and its characteristics of its underside. Peter?
Thank you.
I think this session probably holds the record for the most Peters of anyone.
Yes, it's the Peter principle in Arctic research. What I'm going to talk about is acoustics in a more mundane sense of not using it to probe the properties of the ocean, but simply to probe the shape and thickness of the ice cover, and then what the implications of the discoveries from that are about our understanding of how rapidly the ice cover is changing, which itself leads on to certain consequences of a global kind. So we knew, or my ancestors knew, that sea ice was starting to retreat, and this is the evidence seems to be that it started to retreat in about 1950. Of course, you can't believe a lot of this evidence because before 1950 there was no way of really telling what the sea ice extent was, because you didn't have satellites, you didn't have aircraft coverage, you mostly had a few sealers and explorers sailing around the edges of the Arctic. So these wiggles here are basically your own fantasy. The wiggles after 1950 are real because we then had aircraft cover and satellites. And so it was clear that in the summer months, that's the bottom one, from 1950 onwards, there started to be a linear decay in the area of ice in the Arctic. These are other seasons of the year. It wasn't so obvious because the ice is fast to the edges of the Arctic Ocean and it takes a lot of melt to detach them. So the summer ice is the strongest indicator of retreat. So that carried on until recent years when more dramatic changes started to happen. In 2005, the retreat led to quite a large slot of open water in the month of greatest retreat, that's September. This is the pink line there is the long-term average of the 20th century. Then 2007, an even bigger slice came out and you actually started to have a real sea, a real ocean in the Arctic in summer, with results like warming up of the coastal waters, increase in the wave field, which gives you a lot of wave energy impinging on the ice cover, which may be a factor in accelerating its retreat. That's the subject of a present ONR project in the Arctic. Then 2012 was the biggest jump downward so far, and this produced an ice cover. This compares with 2007, and this is still the record retreat, but as I'll show, the thickness is decreasing all the time, so it's set to make another jump downwards very shortly. So the result of all these rapid retreats was that the area of the ice cover in summer has shrunk much more rapidly than any of the computer climate models predict. These are the suite of models used by the Intergovernmental Panel on Climate Change, and we can see that the actual ice cover in summer now is more than 2 standard deviations away from the median prediction of these models. So something's happened which isn't being taken care of in models. So you have to actually go out and measure things in order to see what is it that's causing the sea ice to retreat more rapidly than any of the factors that goes into a model. So if you're going to measure ice and you want to measure ice thickness, the best way of doing it is from a submarine, because there isn't actually another way. You do have satellites now which measure ice thickness, but what they measure is freeboard of the ice, which is not a very good indicator of total thickness. So since 1958, submarines have been going to the Arctic, and before that, there was a connection, of course, with Walter, like in everything in oceanography, because Walter's supervisor for his thesis was was Sverdrup, and Sverdrup had been to the Arctic in a submarine in 1931 with the first Nautilus expedition of Wilkins, and in the 1950s there were efforts to redo the Nautilus with diesel submarines, and the person who was very strongly associated with that was Waldo Lyon at the Arctic Submarine Laboratory, what became known as the Arctic Submarine Laboratory here in San Diego. And but the earliest suggestions were actually by Walter about using a submarine as a wave measuring tool, that you can use upward-looking sonar from a submarine to measure the distance to the sea surface, so you can measure wave spectra, and also you can measure directional wave spectra by switching between sets of transducers along the deck of the submarine and then steering particular courses. This was all appeared in a wonderful book called Ocean Wave Spectra in 1963, which is still a kind of classic. And I don't think the electronic steering method has ever been tried, but I think it would still work, I think, and give you directional spectra. You could try it from an AUV. Anyway, that was the using submarine for wave measuring that was mentioned at the last symposium, but using a submarine for measuring ice thickness was really a product of this person, Waldo Lyon, and the first nuclear submarine to cross the Arctic was the Nautilus, and he was deeply associated with that, and it collected upward-looking sonar data on ice thickness all the way along its track. That wasn't his intention particularly. He was more interested in submarines as weapons of war, and but he realized that you had to know the distance between yourself and the sea surface or the ice surface, so you didn't hit it. And so that he collected a record right across the Arctic, and that was published as the first data on ice thickness, really good data on ice thickness in the Arctic. It was a pretty crude sonar, but it worked. So then the US collected more data, and then Britain came in, and we heard talk yesterday about should you have academics on Navy ships, or should the Navy build its own research ships? So I was a case, I guess, of an academic on a Navy ship. But I think that only ever applied to submarines. They don't have British academics on surface ships, but only on submarines. So when we started to go to the Arctic, we started to collect upward-looking sonar data, and you can see suddenly there's a kind of revelation when you see your first, or generate your first upward sonar profile, because you can see that in a way that you could never do before, just how formidable the underside topography of the Arctic is, or was. This is multi-year ice, so it's a was. And in the past, people drilled holes in the ice. So Nansen drilled 15 holes during the Fram drift for over 3 years and inferred what the mean thickness of the Arctic Ocean was from that. So it wasn't a very good value. But you can see that more than half of the volume of the Arctic ice is contained in the pressure ridges. That's where what happens here is that the ice can break up with the wind stress to give you a lead, which refreezes, and then a change in the wind stress compresses that, closes it up, and takes you from that to that, a pressure ridge which may be 30, 40 or 50 meters deep. So you have this formidable landscape of pressure ridges interspersed by the undeformed ice. This is undeformed multi-year ice, which is about 3 meters thick and quite rough. So this is what you get, and of course immediately you want to start doing something with this data, because this is cleaned up and fed into a computer. You can then think, well, how much undeformed ice is there? How many ridges are there? How far apart are the ridges? What's the statistical properties of this ice underside? So I was able to develop these analyses over the years of going to the Arctic in submarines. When you go to the Arctic in the submarine as a civilian, the Navy treats you very well. You get a luxurious bunk to sleep in, which is slotted into a torpedo stowage rack. So you don't have a huge amount of headroom, and nor do you have much space. You get to cuddle up to missiles. That's the and there isn't a lot of wall space to hang your photographs. There isn't actually any wall space at all because everything is covered with instrumentation. So that's life on board a submarine, which you have to have a voyage of maybe 7 weeks like this. But the compensation is occasionally they let you out and they dump you on the ice so that you can actually observe and measure the interaction between the ice and the submarine as it surfaces in the lead. So that's always an exciting thing to see. Here it is. Because you have to have faith that they'll come up in the right place, not underneath where you're standing. And there it is coming up through the ice and reaches the surface safely. So that's life on a submarine. And the results out of those, the analysis of this data gives you a probability density functions of the ice draft with a big peak at the preferred draft of the ice type that dominates, whether it's multi-year or first year, and a tail which always has the same shape, and when you plot it out on a semi-log plot, it's a very nice fit to a negative exponential distribution. There's a lot of laws governing sea ice statistics which are very closely obeyed by sea ice, but we don't know the reason for any of them. So we still isn't an explanation for why should the tail of the distribution be a negative exponential. It's also the case that when you look at that tail, the slope of the tail depends on, in this case, depends on latitude. This is several different latitudes down the East Greenland coast. And of course, the further south you are, the more rapidly the ice melts, especially ridges, so that the tail has a greater slope to it. But also you can measure the individual pressure ridges and look at their distribution of heights or distribution of depths. And here we can see that a region with multi-year ice present, north of Greenland, has deeper and more frequent pressure ridges than first-year ice regions. And we now know that multi-year ice, which used to dominate the Arctic when I was first up there, is now almost gone. So the Arctic has switched from this sort of distribution of roughness elements to this sort of distribution, complete change. And as Peter said, as Peter Michalewski, that's changed everything, certainly in terms of acoustic propagation and the roughness of the ice underside surface for acoustic measurements. The pressure ridge count as well fits a negative exponential. This is the distribution of depths of individual pressure ridges, which if you plot them on a semi-log plot, you get the same thing. So you also have a negative exponential there. But the other statistic that's different is if you count the spacings between successive pressure ridge keels, then you find that fits very nicely a log normal distribution. So this is kind of a statistician's paradise that sea ice, most things in geophysics vaguely fit something, some distribution, some power law. But in the Arctic, they really obey the log normals and negative exponentials, and we still don't know why. You can do grid surveys with a submarine and look at small scale statistics. This is actually a submarine at the pole, and then you can now compare the upper surface with the lower surface because we now have airborne scanning lasers which give you a very nice map of the top surface of the ice, which can be compared with the underside. This was some early work we did with a more traditional laser, and finding that the probability density function of the surface and the bottom fit very nicely right up through the whole range of thicknesses, as long as you multiply by a factor of, in this case, 7.9. But the factor changes with time of year because it depends how much snow there is and how much melt has gone on. So it's not a constant factor. Otherwise, you'd only ever have to fly around with a laser and you'd know your probability density function. The first evidence from all this that things were changing, it took us a long time to try and establish these relationships. So eventually I started to realize things weren't staying the same. And this is the difference between the probability, between the mean draft of ice in a big slice of the Arctic that we covered with a grid pattern from the Submarine in 1976 and in 1987. And we can see that so in 1976 there was a lot of pressure ridging developing against the north coast of Greenland, so you had high mean values. In 1987 they were lower, and this is inset is 2004, and they were even lower. Here they were 5, 6, 7, here they were 4 to 5, here they're 2 to 3 meters. A massive loss of average thickness in this sector of the Arctic, and this was, so this paper I wrote on that was the first paper that showed that the ice was thinning in the Arctic. And it was a very big thinning. It was about 15% then. It's now more than 40%. So the Arctic ice thickness is only about half what it was in the 1980s. And this was backed up by an analysis of more extensive US data, which was from the Beaufort Sea part of the Arctic mostly, but other regions as well. This was by Drew Rothrock, and he found this same very large decrease, whichever region of the Arctic you looked in, there was a big decrease in thickness. So the question is, what's caused that? And Peter's shown this big warming of the Atlantic layer in the Arctic, and so the question is, was heat flow from that the cause of this warming, or was it warming of air temperatures? So it's still a problem that we're not absolutely certain about. The interesting thing about the UK data, where we've been able to help, I guess, and work with the Americans, has been that the data that's collected by American submarines and is released is within a box called the Gore box, because it was a committee chaired by Al Gore that set up this, and it was a region that's away from all other national claims, so it's absolutely definitely international waters. But the British Navy kind of ignored international waters and collected data from Fram Strait and from this region just north of Greenland and Ellesmere Island, where there's a lot of multi-year ice still remaining. So in a sense, our data was able to complement the US data. But if you put that together with the area data, you get a thinning and a decrease in volume, which is quite startling. It's much faster than linear. It's looking like an exponential decay, and the result has been that the volume of ice in summer now is about a quarter of what it was in the summer of about 1980. So there's much less ice in the Arctic now, and the summer ice is only a quarter of its original volume. And this was expressed nicely by Marc Serres in a thing he called the Arctic death spiral, which is that you take the volume of ice in each of the months of the year, and then you go around the clock with years. So you start in 1979 and come around to the latest year you've got data for, and you can see if conditions weren't changing, these would be concentric circles, but since they are changing, it's a spiral coming in towards the centre, with September set to reach the centre first, followed by August and November, and October rather, and then the winter months are also spiralling inwards, so that the whole volume of the ice in every month of the year is decreasing. It's just that the summer months will hit zero first. And what does that look like? And this is what the Arctic looked like in 1970, first time I was up there. This is the Canadian ship Hudson. And this is summer ice. It's all broken up, and this is just north of the Alaskan coast. And it's broken up, but it's very, very thick. This is multi-year ice. It's 3 meters thick. It's a formidable obstacle, even in summer. So this ship could only just push through it, couldn't break it. And then this is 2014, same place, actually further north, and with the Healy. And this ice is really very, very thin. It's, in fact, the following week it disappeared. It's so thin you can't walk on it. It's just slushy ice. It's the same. This is further north in the same part of the Arctic in summer. So that's what the difference between the 1970s and now is in the Arctic. It has other impacts. This, for instance, this is first-year ice in northwest Greenland, where Karnak, where you still have Eskimo hunters using dog sledges, and they've been falling through the ice because it's got so much thinner. Now, actually, in a project I'm involved with, we've fitted radar to the base of some of their sledges, so they can track ice thickness as they go along and transmit the data back by satellite. And they get a warning as well if the ice gets thinner. But then the other thing makes it more difficult to now do science in the Arctic. This is in the middle of, because the ice is so much thinner, it means that it's much easier to break it up with wind stress, and you get patterns of breakup extending across the entire Arctic. This is the whole Beaufort Sea from Banks Island to Alaska, and in the middle of winter, in March of 2013, it's completely broken up, and these are all leads. Now, the problem with that is if you're having ice camps, like these wonderful Atlas ice camps, which everybody's used, set up by APL in Seattle, you can see, well, here's a helicopter, but in fact these camps are set up and maintained by fixed-wing aircraft, and it's very hard to find a safe runway now, which isn't going to break up on you in the middle of winter. And so that today, if you do the latest ice experiment that we were involved in, called IceArc, used a ship. Everybody, and if the ice broke up, everybody would get into the ship rather than have a distributed camp. So that's what we managed to do with just upward-looking sonar. So going back to the acoustic technology, the next type of sonar that we put on submarines was the second dimension, which is side scan, so it gives you a shadow view of the underside, and this immediately tells you the difference between first-year and multi-year ice. These are multi-year flows, and they're covered with what looks like lunar craters, and they are actually craters. They developed in previous summers by meltwater pools on the ice surface absorbing solar radiation, causing the ice on the underside to melt more rapidly, giving you inverted craters called under-ice melt pools. And when they refroze, you still have the shape. So multi-year ice has a rugged bottom because of these previous summers of melt, reflecting surface melt. And so you can see the difference between multi-year and first-year ice, which has a smooth bottom. I just thought I'd show this because we found when we put instruments on a submarine to do it, they tend to get then taken up by the submarine and for future voyages, and they use them. So they used this one operationally, and this shows an approach to an iceberg, which is the white thing here, because you don't want to approach an iceberg too closely, but if you find one, you go around it to map it. So this is the upward-looking sonar, and then this is the side scan sonar. The only trouble with all of this is that it tells you there it is, and it's the big, thick, deep thing there in that top right-hand picture. That's a 75-meter deep iceberg. Deeper than any pressure ridge, but of course what you lack is predictive ability. You know it's there, you know you just avoided hitting it, but you couldn't see in advance that it was there. So the next thing the final thing we've moved to with submarines is multi-beam sonar, the same way as you now use multi-beam routinely for mapping the seabed, we were able to put one in this sonar dome and collect under ice data from that on a crossing in 2007, which was actually the last Arctic trip that the Royal Navy has done up to date. So you get the same, you now get this wonderful three-dimensional view, so you can, for every time there's a ridge, here's a ridge with a lead running through it, you can map the shape of the ridge, the depth of the ridge, the slope angles of the ridge. It's just wonderful. It's a whole new view of the underside of ice that we never had before. Now we have to work, we work more with AUVs mainly because submarines not being available, at least from Britain. AUVs give you even better quality because you're flying the AUV much closer to the ice than you're flying the submarine, because there aren't any people on board. And so you can get this very nice quality. This is a section across a multi-year ridge, 33 meters deep, with another ridge coming into from one side. You can see the individual ice blocks, and it's a very nice picture. And if you look at a lot of them, you can then look at the statistics of pressure ridges, but know that which ones are first year and which ones are multi-year. The narrow ones are first year, and the wider ones are multi-year ridges. So again, there's a whole new view available from multi-beam sonar that we didn't have before. And for small-scale use, if you're doing an experiment like this is the Atlas experiment in 2007, where we were working on that as well as going underneath it with a submarine. And here you can map a small number of ridges by simply using an AUV from a hut and putting out, or building your own hut, of course, and putting the AUV out, and it will give you a very nice view of the underside of the ice. Again, very, very high resolution, so you can see individual ice blocks here. Here we had a diver go down to show that really wasn't noise, that was actually individual ice blocks picked out by the Kongsberg sonar. And here's we're going a transition into a multi-year ridge, which is much more solid, large blocks, and the first year some pinnacles here, which don't have very much strength. So what's happened in the Arctic, it seems, from all the data we've been collecting, is that two things have happened. Firstly, the ice itself has got much thinner. The natural growth regime is thinner. This is the old May-Cut-Untersteiner view of how ice develops over many years. It grows to 1.5 meters in the first year. It melts a little bit. It gets thicker and reaches an ultimate thickness after many years called the equilibrium thickness, which is about 3 meters. This is the traditional view, and it's completely gone now because, firstly, it doesn't reach that thickness anymore because of warmer air temperatures and potentially the impact of warmer water underneath. It doesn't get as thick and it melts more. So this becomes a curve where it can't really get to very much of greater thickness. So we don't have any more of these wonderful views like Peter showed of multi-year ice. But not only that, because there's less multi-year ice around, this multi-year ice used to be dominant in the Arctic, then you can detect it by satellite, and it used to be the red stuff was multi-year ice. And then during the first decade of this century, it just diminished until now there's almost none left. So the ice is younger, so it's thinner anyway, and there's a change in the surface circulation of the Arctic means that ice tends to exit through Fram Strait before it gets very thick. So it's younger ice everywhere, and it's thinner as well. So it's thinner for two reasons. So what does that do? I'll quickly go through what it does. There's immediate impacts of thinning, and one of them I'll just mention is the Atlantic thermohaline circulation, which Jim Lynch mentioned yesterday. This is a very crude picture of it. This Carl Woodjoy objects to this because it's a grossly oversimplified view of the thermohaline circulation, which is really broken up into a lot of different cells. But it is the circulation that's driven by heat and salt salinity rather than by wind. But if we look at the Atlantic bit, there is a net flow across the North Atlantic from the Gulf towards Northern Europe, which is in the same direction as the Gulf Stream, and just strengthens the Gulf Stream. And then somewhere in the north, the water sinks, and you have a return flow southwards. And there's two places where this seems to be happening. One is in the Labrador Sea, driven by cooling in winter, but the other is in the Greenland Sea and was driven by freezing in winter. And the region is a very interesting area called the Odden Ice Tongue, which is an ice tongue that grows in winter from the edge of the East Greenland Current, and in the middle of this ice tongue, at a very exact location of 7500 north and 000 west, God designed the location of deep convection in the North Atlantic as an easy to get to location, and under that ice tongue you're getting the formation of chimneys, which is a way in which the surface water is sinking towards the seabed, and that's driven by the fact that the ice tongue is a place where you have ice growing locally in the form of pancake ice, where when there's a lot of waves present, the ice can't form a sheet but forms pancakes. But these pancakes grow very fast and reject a lot of salt back into the ocean, and that increases the salinity of the surface water just enough to achieve an overturning. And so what you were getting was overturning of the water within this very limited region in the centre of the Greenland Sea Gyre, and that was giving you these amazing cylindrical rotating cylinders called chimneys going down to, in this case, 2,500 metres. And here it's cutting down through some warmer water on either side, and it shows in the salinity and density. So they are amazing features. They're long-lasting, a bit like meddies that we heard about yesterday, but sort of similar. They're long-lasting rotating features. And here we see the -1 degree contour of a chimney cutting down through a -0.9 degree layer. So they really do look like chimneys, especially if you show them in red. They look like chimney pots. So they look even more like chimneys. But the problem has been that the ice isn't forming anymore in that area, so we're not getting any chimneys, and the result, according to the predictions of the European Environment Agency, are that will give you a cooling of northwestern Europe. So Britain, Iceland won't get the same amount of heating that the rest of Europe will get. The predictions, this is a prediction by a model, that business as usual model, which is that we're all going to be subject to about 4.5 degrees of warming by the end of the century, which will be pretty disastrous. But Britain will only get about 2 degrees of warming. That's at the expense of the Gulf region, which gets, because there's less water coming up, warm water coming up from the Gulf, you're going to get more heating in the Gulf, and that means you're going to get bigger and nastier hurricanes. The other things that I'll have to mention in 2 minutes are that the other consequences of thinning and retreat are that the albedo is reduced of the planet because of the extra amount of open water. This was modelled by a group from Scripps, Stoney, Eisenman, and Ramanathan. They didn't take account of the fact that the snow line's also retreating, and you're getting much less snow, which also has an albedo impact. So if you sort of double their estimates, you get what is really likely to happen, which is equivalent to about 50% added to man-induced greenhouse gas addition. Another effect will be that as we saw from Bruce's talk this morning, Greenland is melting, and the warmer water, the warmer air over the newly ice-free Arctic Ocean is giving you surface melt in Greenland. This was in 2012, you had surface melt over the whole surface. This is giving you an increased rate of loss of mass from Greenland. This is shown by a gravity satellite, and therefore we're constantly increasing at the predictions that we're making about how much sea level rise there's going to be in the future. So I'll sort of end with another Walter thing here, which was that when I talked to Walter about some of these things that are coming out of these measurements, he realised and said, well, look, sea ice is retreating and it's melting and it's thinning. That means your sea ice is disappearing, and that means you're adding fresh water to the ocean, but you're not causing any sea level rise directly by that because the water's already afloat in the form of sea ice. So you're diluting the ocean without causing any sea level rise. But at that time, this was 2004, a favourite method of calculating sea level rise or estimating was Levitus's work on census hydrography, and that said, well, the ocean is getting diluted because of retreat of the Greenland ice sheet. So we measure the ocean dilution, we can measure sea level rise, or the contribution to sea level rise from loss of mass into the ocean. So we did that sum, and it turned out that it worked, that you got that the Levitus system worked with Greenland ice melt, but it also works with just sea ice melt. So there's something wrong, that the amount of sea ice melt that's happening every year is just enough to cause, to account for the observed dilution of the ocean. But that dilution is supposed to be due to Greenland ice melting. So there's something wrong, and so we concluded there is something wrong. There's an anomaly that hasn't been explained, so we wrote a paper on it, and the anomaly, nobody has come along and explained that anomaly since then, so we're still waiting for that to be explained. So I'll skip over the last thing here, which is methane being emitted from the Arctic, which is another consequence of global of ice loss that is very, very serious and could actually give us a big boost. So, and I won't even mention Hurricane what's his name, because that's also thought to possibly be due to retreat of sea ice, because it reduces the strength of the jet stream because of the contrast between the Arctic and the lower latitudes, and that could really have an impact on crop production. So all these later effects, which I skimmed over because I'm being threatened by Peter here, you can find for yourself by reading my book, which was coming out next week, called A Farewell to Ice, available in all good bookshops. So, I'll end there. And so the moral is you need to do observations at sea and in the Arctic, and you still need to do things, primitive things like going underneath with submarines and vehicles and using sonar, and the things that tells you are sometimes rather frightening about what's happening to the world.
I'll allow one question while I change over. Anyone have a question or comment for Peter? No? Thank you, Peter.